Good morning. This project is on the development of 3.3 kV silicon carbide planar gate power JBS FET. Two organizations are involved in this work. SiCamore Semi, which is a new silicon carbide foundry located in Bend, Oregon, and this work at SiCamore Semi is under Dr. Michel Francois and North Carolina State University, and this work is under Professor J. Baliga. This device is consistent with Power America request for proposals to fabricate devices in open foundries with breakdown voltages above 3.2 kV. The project started in February on February 1st, 2020, and it is on track to be completed by November 30th, 2020. North Carolina State University has previously developed with another fab a Gen 3 precise chip design and process technology for 1.2 kV devices. And precise stands for process engineering for manufacturing silicon carbide electronic devices. In this project, NCSU is creating a Gen 5 precise TM chip design and process technology at SiCamore Semi to manufacture 3.3 kV rated silicon carbide planar gate power JBS FETs with reduced specific on resistance of silicon carbide power MOSFETs, also integrating JBS diode with MOSFETs at 3.3 kV level. In this work, SiCamore Semi will be a second source foundry in the US, and this new technology, this project will allow us to retain silicon power MOSFET technology leadership in the US. As a path to market, we would like first to complete the development work and prove in the process at SiCamore Semi. Then manufacture first silicon carbide planar gate power MOSFETs with integrated JBS diodes at the 3.3 kV level for higher power application at SiCamore. SiCamore Semi will then be qualified as an additional US-based foundry. This proven technology will then be available to companies that would like to manufacture these products. Silicon power devices manufacturers could license this Gen 5 precise TM technology from North Carolina State University, and by doing this, we will enhance commercializations and bring down device costs. This slide shows the mass designed by North Carolina State University for the fabrication of 2.3 kV JBS FETs. There is a total of 25 devices on this mass. On top, there are a couple of JBS diodes, and there are approximately in total 17 power MOSFETs with different cell designs and also 6 JBS FETs devices with different cells designs, including also is a baseline device, which is MOSFETs number 16. After looking at the design, the mass, and generate the mass, we went over the high-level process descriptions and then wrote the detailed process run sheet that should be used in the fab. Before processing the latch, we have run few short loops to verify certain critical parameters to see how close we were from simulated values. We run a gate oxide experiment with proper annual cycles and gases, measure the breakdown voltage, obtain the CV plots, and measure also the gate leakage, gate leakage after powder deposition, dope, and pattern. Parameters such as junction depth, implant profile, surface concentration for various implantation were measured after high temperature anneal, and front and back nickel depth and silicidation were evaluated at different temperatures. These short loops were done during the first quarter of this project. There are 18 blocks in this process. Block 1, for example, started as scribe, and all the way to block 18, which is the back metal, which is the final process step. And by block, we mean it's not only just one step. For example, if we take the P plus block, the block 6, that involves clean the wafers, oxide deposition, which is a PCVD oxide deposition, then densifying it, and then coat, expose, developed, UV baked, and after developing a UV bake, we do a hard mass oxide etch and strip the photoresist, do the implant, and strip the hard mass, which is the oxide hard mass, and then inspect the wafers. So that involves a lot of sub processes in the block. This is the project timeline. After the completion of the first lot, the wafers will be shipped to North Carolina State University, and they will be probed and see if there is any modification to make in terms of implants or process steps. And then we will adjust the process based on this on the final test here, and then run the second lot, and that will be sent after at completion to North Carolina State for final measurements. Then to recap, the goal was to create a NCSU Gen 5 precise CM chip design and process technology in partnership with SiCamore Semi for manufacturing 3.3 kV rated silicon carbide planar gate power JBS FETs. We were supposed to produce 2 lots, and the deliverables are statistical data with maps, and then send a few JBS FET die to device bank. On the right side here, you could see the cross section of the JBS FET, and the JBS diode is there, and then the MOSFET is here. And really the market segments impacted will be industrial motor drives, traction drives, and the outcome of this project will serve as the baseline process for Power America members to design their own product by licensing the Gen 5 precise process. And accomplishment outcomes, so the technology readiness level at the beginning will be 7, and at the end At the end or at the completion of the project, the technology readiness level will be 8.